China's Air Force says they may have figured out how to land a hypersonic drone.
China has recently stunned the aviation world with an announcement that feels straight out of tomorrow's science fiction. The unveiling of its hypersonic jet, the Nanchang No. 1, a revolutionary aircraft capable of flying anywhere on Earth in under 2 hours. This concept of point-to-space travel isn't a distant fantasy anymore. It's a carefully engineered plan where passengers board a sleek vehicle that launches above the atmosphere, cruises at unimaginable speeds, and brings them down at a distant city before they've barely finished a cup of tea. While the idea of hypersonic passenger jets has floated around aerospace circles for decades, what sets the Nanchang No. 1 apart is how real and tested it already is, backed by years of design studies, computer modeling, wind tunnel testing, and small-scale prototypes that have shown not just promise but real performance. The star of this machine is its multi-ducted twin-turbine ejector ramjet, or mutter engine, an intricate fusion of turbofan engines for takeoff and subsonic cruise, rocket boosters to push through the supersonic barrier, and ramjets and scramjets that come alive as the jet streaks into the hypersonic realm of Mach 6, roughly 4,600 miles per hour or over 7,400 kilometers per hour. To put this speed into perspective, it's 6 times the speed of sound. A New York to London hop that today takes 7 hours could be sliced to under an hour, completely redrawing global maps of trade, tourism, and geopolitics. But speed alone isn't the whole story. The aircraft's design demands materials that can survive temperatures soaring beyond 1,500 degrees Celsius (2,700 degrees Fahrenheit), generated by the sheer friction of air molecules smashing into the craft's leading edges. To tackle this, Chinese engineers turned to next-generation ceramic matrix composites, materials light enough for flight but robust enough to shield the vehicle's skin, electronics, and fuel tanks from destructive heat. The Nanchang No. 1's real brilliance lies in its multi-stage propulsion system, which orchestrates these engines in a carefully choreographed sequence. Turbofans lift the jet gently into the sky. Rocket engines roar to push it past the supersonic wall. Then air-breathing ramjets and scramjets sustain the cruise at hypersonic speeds where normal jet engines would simply choke. This laid approach gives the jet the flexibility to operate safely at every stage of flight, from runway takeoff to high-altitude sprint. What's even more striking is that this isn't an overnight breakthrough. The project has roots stretching back to 2019, led by Chief Scientist Yin Zhong and the Aero Engine Corporation of China, and built on decades of earlier military hypersonic research and aerospace engineering advances. Yin himself has described it as a breakthrough that could change how human civilization thinks about global travel, a claim that feels less like marketing and more like sober assessment when you consider the aircraft can carry up to 10 passengers and could enter operation as early as 2025. Unlike the iconic Concorde, which reached Mach 2, 2,179 kilometers per hour, and still wowed the world until its retirement in 2003, the Nanchang No. 1 aims for speeds nearly 3 times higher, with smoother engine transitions, better fuel efficiency, and advanced heat shielding. But this race for hypersonic dominance isn't China's alone. Across the globe, aerospace companies and governments are locked in a new technological arms race, each chasing the promise and the power of hypersonic flight. American firms like Hermes, Stratolink, and Hypersonics in Australia have joined forces with defense agencies, pouring billions into prototypes, small-scale demonstrators, and radical engine concepts. Russia, meanwhile, has made headlines with its avant-garde hypersonic glide vehicle, reportedly capable of Mach 20, and its Kinshal A-launched missile hitting Mach 10. The strategic stakes couldn't be clearer. Hypersonic aircraft and weapons are seen as nearly unstoppable, able to outrun most missile defenses and transform military balance overnight. Beyond military implications, the commercial potential is equally breathtaking. Imagine business travelers jetting across continents in under 2 hours, or cargo flights turning overnight shipping into overlunch shipping. Even long-haul flights like Sydney to Los Angeles, which today test human endurance at 14 hours, could be reduced to a quick jaunt that barely interrupts a workday. Yet the challenges are formidable: controlling heat at hypersonic speeds, designing engines that breathe thin, fast-moving air without stalling, and protecting passengers from G-forces and cabin heat. Engineers are turning to futuristic materials like ceramic composites and active cooling systems to shield vital structures. Meanwhile, NASA's X-59 project with Lockheed Martin is trying to tame the sonic boom, a thunderous crack that has kept supersonic commercial flights over land grounded for decades. By reshaping the fuselage and carefully guiding shockwaves, the X-59 aims to create a low-boom profile that might let faster-than-sound jets fly over cities without rattling windows, a step toward making hypersonic passenger flights widely accepted, not just technically possible. The promise of hypersonic flight also reaches toward space. Engineers envision reusable hypersonic vehicles launching small satellites more cheaply and quickly than rockets, with prototypes like Hypersonics' Delta Velo's orbiter showing how these platforms could revolutionize orbital logistics. And it's not just hardware. Advanced AI systems, real-time data feeds, and digital twin simulations help engineers predict engine wear, manage airflow at extreme speeds, and keep pilots and passengers safe. The race is intense. Russia, the US, China, Australia, and European nations all funding test flights and next-generation engines, while the global aerospace supply chain pivots to produce high-temperature alloys, ceramic tiles, and rocket-grade composites. In the middle of this, China's Nanchang No. 1 has already raised the bar, demonstrating real, near-market readiness while many rivals remain in the wind tunnel. With a working prototype that has already reached hypersonic speeds in tests, a small passenger cabin designed for elite business or leisure travelers, and a roadmap to operational service in the near future, it's both an engineering feat and a national statement. The vision goes beyond shrinking travel times. It hints at a future where hypersonic flight becomes as routine as long-haul jets today, where the Earth feels truly small, and where aerospace technology drives the next industrial revolution, reshaping commerce, military power, and even human culture itself. And as other nations scramble to catch up, from Russia's Mach 20 ambitions to the US's dual focus on military and commercial applications, it's clear the Nanchang No. 1 is more than just an aircraft. It's the opening move in a global race to redefine the very meaning of distance, time, and what it means to move across our planet. The competition is fierce, the stakes are enormous, and the next few years could decide whether hypersonic flight stays a technological curiosity or becomes the new standard that shrinks the globe forever. The global race to conquer hypersonic flight has quietly transformed from the ambition of a few advanced nations into a sprawling, high-stakes contest drawing in players from every corner of the world. While countries like the United States, Russia, and China dominate headlines with jaw-dropping prototypes and defense programs, Europe is making bold strides with projects like France's VMAR X, Vehicle Maneuvrant Experimental, designed to pioneer maneuverable hypersonic weapons and aircraft that could redefine future aerial combat. Meanwhile, India, driven by its own Make in India vision, has stunned observers with successful tests of its hypersonic technology demonstrator vehicle, a testament to Indian scientists' determination to place the country firmly in this next frontier. Yet, beyond the excitement of record-breaking speeds and futuristic engineering, hypersonic travel stands at the edge of what's possible, where physics, economics, and politics collide in spectacular and often sobering ways. Imagine this: boarding a sleek, needle-like aircraft in Tampa and arriving in Beijing, Sydney, or Tokyo in under an hour. Researchers at places like the University of Central Florida are pouring years of work into making such dreams real, experimenting with airflow dynamics, heat management, and propulsion systems that sound like science fiction. The promise is intoxicating. Business travelers skipping between continents before breakfast, urgent cargo shipments arriving across the world in minutes, and scientists launching into near space on reusable craft as easily as boarding a train. Yet for every promise, there's an equally formidable challenge that threatens to ground the entire endeavor before it even takes off. Cost is perhaps the most immediate and unavoidable obstacle. Designing and building even a single hypersonic prototype, capable of flying sustainably at Mach 5 and beyond, demands billions of dollars in research, specialized materials like ceramic matrix composites to withstand searing heat, and revolutionary propulsion systems that blend turbofans, rockets, ramjets, and scramjets in seamless harmony. Mass production, which would require specialized factories, global supply chains, and enormous quantities of rare, heat-resistant materials, only amplifies the expense. Even with optimistic projections, industry experts warn that a single seat on an operational hypersonic passenger jet could cost upwards of $100,000. While corporate executives and VIPs might justify such cost for speed, it's hard to imagine this becoming an everyday travel option for most of humanity. Operational expenses, from staggering fuel consumption to frequent, meticulous maintenance to repair heat damage, threaten to keep prices sky-high long after the technology itself matures. And then comes the noise problem, a barrier that even the legendary Concorde couldn't overcome. Supersonic booms rattled windows, startled wildlife, and drew bands from overland routes, forcing the Concorde to fly mostly over oceans. Hypersonic jets, traveling several times faster than the Concorde, risk producing even louder, more destructive shockwaves. NASA's X-59 program is exploring aircraft shapes that could transform an ear-splitting boom into a softer thump, but these designs remain experimental and largely unproven at hypersonic speeds. Without credible solutions, countries with strict environmental and noise regulations might refuse to open their airspace, drastically limiting routes and commercial viability. Heat, however, looms as the single greatest technical dragon to slay. At Mach 5 and beyond, air molecules smash into the aircraft surface, generating temperatures exceeding 2,500 degrees Celsius (4,532 degrees Fahrenheit), hotter than the melting point of most metals. Keeping passengers and critical systems safe demands thermal protection systems so advanced they rival space shuttle technology. Engineers have designed variable thickness thermal shields and developed exotic materials like carbon-carbon composites to radiate heat away quickly. Yet even these approaches face unpredictable dangers. Aerodynamic turbulence can create sudden, localized heat spikes, and the aircraft's own electronics, from flight computers to cabin systems, generate internal heat that can't simply be radiated away. If these systems overheat mid-flight, catastrophic failure could follow, a terrifying prospect for any passenger. Beyond physics and engineering, there are profound practical constraints that further dim the commercial dream. To stay light enough for hypersonic speeds and carry the required fuel and cooling systems, current designs can only fit a handful of passengers, sometimes as few as 10 seats. Unlike today's wide-body jets that distribute costs over hundreds of passengers, a tiny hypersonic cabin forces ticket prices to soar even higher. Even airlines, used to thin profit margins, could struggle to justify such niche services. And while wealthy executives or celebrities might pay for the privilege, it's hard to see how this model could scale into a meaningful share of global air travel. Then there's the environmental impact, which threatens to make hypersonic flight not just a technological challenge, but a political flashpoint. Hypersonic engines burn enormous quantities of fuel, and the emissions they produce occur at higher altitudes, raising concerns about ozone layer depletion and long-lived climate effects. In an era of carbon-neutral pledges and growing public scrutiny of aviation's footprint, introducing a class of aircraft that burns more fuel per passenger than anything before it could meet fierce opposition. Even if the carbon impact were mitigated, the environmental damage wouldn't end there. High-altitude emissions, contrails, and potential chemical interactions could further warm the planet or erode the protective ozone layer that shields life on Earth. The final frontier of obstacles lies in regulation and safety. Aviation authorities like the FAA and EASA have spent decades refining standards for subsonic and limited supersonic flight, but hypersonic speeds introduce hazards so unique that entire rulebooks must be rewritten. At Mach 5, emergencies unfold in seconds. Conventional strategies like slowing to glide aren't possible, and safe abort systems remain largely theoretical. Certifying aircraft that fly so fast, so high, and so differently demands years, if not decades, of rigorous testing and international coordination. And the political climate surrounding advanced aerospace technology, often linked to defense and national security, could add further delays. Yet despite these formidable barriers, the race continues with relentless energy. China's Cheng No. 1, aiming for Mach 6 travel by combining turbofans, rockets, and ramjets, embodies the audacity of this vision. Designed by leading scientist Yin Zhong and backed by extensive R&D since 2019, it plans to start test operations by 2025, hoping to carry 10 passengers at speeds that would eclipse even the Concorde threefold. Russia's Avangard and Kinshal systems prove the military sees hypersonic technology as strategically transformative, making it nearly impossible for missile defense systems to intercept. In the U.S., private firms like Hermes, Stratolink, and Hypersonics, alongside government-backed DARPA and NASA, are chasing their own designs, from quiet supersonic passenger planes to hypersonic cruise missiles and reusable orbital vehicles. Europe, through programs like VMAR-X, and India with its demonstrator vehicle, further underscore the truly global nature of this technological frontier. As the world moves deeper into the 21st century, the question is not just whether hypersonic travel will happen, but what form it will take, and who will benefit. Will it remain an exclusive, high-cost luxury for the few, a military advantage for powerful nations, or can engineers and policymakers overcome the towering hurdles to make it safe, sustainable, and accessible to many? For now, the dream of boarding a flight in New York and stepping off in Tokyo for lunch remains tantalizingly out of reach, tangled in heat, cost, noise, environmental fears, and regulatory caution. But every day, researchers chip away at these obstacles, drawing us closer to a future where hypersonic speed reshapes not just travel, but how humanity understands distance itself. So what do you think? Are we on the brink of a new golden age in aviation, or chasing a horizon that might never fully arrive? Share your thoughts in the comments. And if you enjoyed this deep dive, don't forget to like, share, and subscribe for more explorations into tomorrow's technology. And while you're here, check out the next video on your screen. You'll find it just as fascinating.